Hi, I'm Mrs. Calvin, and this is the 1.3 Chemistry Notes on Accuracy and Precision. In this set of notes, we are going to talk about the difference between accuracy and precision, how we can quantify accuracy using an equation, how we determine the number of digits that are significant, and then perform calculations using these. So accuracy and precision are terms that are used kind of interchangeably in everyday life, but in science, they actually both have different meanings. They are going to express how accurate or they are going to communicate information about the measurement that we've made. So accuracy is defined as the closeness of a measurement to the correct or accepted value. So for instance, if I was wanting to know what the mass of a specific quarter was, I would put it on a scale and I would have a measurement, so 5.67 grams. And then I could look up what that quarter should weigh. And so US Treasury here, quarters weigh 5.670 grams. And so this would be an accurate measurement then. So in this example here, we have different dartboards, and so the dartboard that illustrates the highest amount of accuracy is dartboard D, because all of the darts are on what we call the bullseye. Now precision is slightly different. So in precision, we would actually need more than just one data point to say if something is precise. So accurate is how close it is to the accepted value, our target. Precision is the closeness of a set of measurements to each other. So if I measured that quarter 3 different times, and I got 3 different measurements here, 5.67, 5.80, and 5.05, then how close they are to each other would be my precision. And these are not very close, so this would not be a very precise instrument. So going to the example of the dartboards again, the ones that are going to be considered most precise are the ones that are grouped, the series that are grouped. And so D has all 4 darts closely grouped, but also B. So B, even though it is not on the bullseye, the darts are close together, and so both of these would be considered precise. All right, so let's say we have 3 students who are needing to measure the density of an object. And so the 3 students all measure the density 3 different times, so we have 3 different trials. Now, we can say something about the accuracy and the precision of their measurements. So in order to say if something is accurate, we have to have an accepted value for that. So in this one, our accepted value is 1.59. Now, for each student, they have different measurements. And so to compare to the accepted value, the experimental value that we're going to use is not the values from the trials. So it's not these. Instead, what we're going to do is we're going to use the averages. So averages are going to be used to quantify accuracy, whereas precision, remember, is a series of measurements. And so the different trials, we're going to look at those to determine the precision. So in this question, given the accepted density of the object is 1.59, which student's average is the most accurate then? So looking at the 3 different averages, the one that is closest to 1.59 is 1.57. So the most accurate student is going to be A, because its value is closest to the accepted value of 1.59. Now for precision, we need to look at how close the series are to each other. So for instance, for student A, I'm going to look at the highest and the lowest values, and the difference between them is 0.06. For student B, the highest and the lowest value, the difference between them is 0.28. And then finally for student C, the highest and lowest value, the difference between them is 0.02. So for precision, we want the series to be as close together as possible. So whichever one has the smallest range, which is student C, that is going to be the most precise. So student C is the most precise out of this data. Now, for accuracy, we can actually quantitatively state what the accuracy is. And so what we're going to use is an equation called percent error. And so the equation for percent error is the absolute value of the accepted minus the experimental divided by the accepted value times 100 because it's a percent. So again, if we look at the data from the density project, what is student C's percent error? So we have to have an accepted value, and that's right here, the 1.59. So this is going to be my accepted value. And then we also have an experimental value. And so for student C, their experimental value is going to be the average. So to figure out the percent error, we simply take the absolute value, so we're going to ignore the negative sign essentially, of my accepted 1.59 minus the experimental of 1.70. Divided by the accepted value of 1.59 times 100 because this is a percent, and that gives me 6.92%. 6.92%. So that is the percent error for student C. And that's going to tell us how accurate they were. I would, for student A, because it's more accurate, that percentage is going to be even smaller then. So when we are doing measurements, the number of digits that we report is actually a function of the precision of that tool. So here I have 3 scales, and the first scale has a number to the 10th place, whereas the second scale, its last digit right there is to the hundredths. And then finally this last scale has digits all the way out to the thousandths place. And so this one is the most precise and therefore the most expensive too, by quite a big magnitude. So the precision of an instrument is related in how many digits we are going to report. So here we have 2 rulers. They are both centimeter or metric rulers, but we are going to report different numbers for the same yellow stick because the rulers have different precisions. So this first ruler, I know that that yellow stick is somewhere between 12 and 13. So I am sure that it is 12. Now, I don't have any marks beyond that though, in between 12 and 13. So I would have to guess what the tens place is. And so I might guess that it is 5. And so this is my guess. So we will report numbers by reporting the digits that we know plus 1 that we are going to guess. And so for the second ruler, again, I know it's between 12 and 13. So it's going to be 12. And now I have these little marks, and I can see that this yellow stick is on the 5 mark, the fifth, the tenths, 0.5. So I know that one. And then, so it's going to be between these marks that I'm not sure of. Is it exactly on the 5 mark? Is it a little over, or is it a little under? I'm not sure. And so this last digit is going to be guessed, and I'm going to guess that it's on the mark. So it's 12.50. So even though it's the same yellow stick with 2 different rulers, they have 2 different types of precision, and so we will have 2 different measurements. So significant figures are the digits that are meaningful in terms of accuracy or precision. They actually carry meaning for that measurement. They communicate the precision of the instrument that was used to measure it with. And so remember, we report all our known digits plus 1 more that we are going to guess. And so that's why 12.5 is actually not the same thing, or it's not communicating the same thing as 12.50. So if we are doing calculations with these measurements, how do we figure out how many significant figures there are? Well, there's a set of rules that we're going to count on. So the first rule says any number that is not a 0 is going to be significant. So an example of that would be the number 847. The 8, the 4, and the 7 would all be significant, and so this would have 3 sig figs. Now, beyond that, are my zeros. And my zeros can be in basically 3 different locations. So let's take, for instance, this number, 0.0, 120300. So here is my first non-zero number. Here is my last non-zero number. And so the zeros themselves will either be before my first non-zero number, within my non-zero numbers, or after my last non-zero number. And so we give these different names. So these are my leading zeros, these are my captive zeros, and then these are going to be my trailing zeros. So leading zeros will never be counted. So another example would be 0.012. And so the 1 and the 2 are significant, but the zeros in front are not. And so this one would have 2 sig figs. Now, captive zeros are always counted. So just like my digits that are not 0, captive zeros are going to be counted. And so an example of that would be 20,302. So the 2 and the 3 count because they're non-zeros. And then these zeros are in between them or within them, so they also count. So this number has 5 significant figures. Now, it's going to be my trailing zeros, the ones to the right of my last non-zero number, that are going to be a little tricky. Sometimes we count them and sometimes we don't. And what determines if we count it is going to be whether or not a decimal point is present. So an example would be the number 120.00. Now the 1 and the 2 count, and then I have these zeros to the right, what we call trailing zeros. And so do we count them or not? Well, what we have to do is figure out if a decimal point is present. And in this particular problem, there is a decimal point. It is present. And so yes, it would be counted. So this number would have 5 significant figures. Now let's take the same, essentially the same numbers, 1, 2. Then this time it's going to be 12,000 though. So 12000. So again, the 1 and the 2 count. I have these zeros that are behind them or trailing, but in this number there is no decimal point present. So no decimal point, and so that means that we will not count them. And so 12,000 only has 2 significant figures. All right, so when we know how many significant figures we have and we do calculations with these measurements, we will need to round some numbers, maybe we'll need to round some numbers down. So with the rounding rules, remember if the number, let's say for instance, we need to round this to 3 significant figures. I'm going to start on the left-hand side. So the 2, the 5, and the 3 are the 3 significant figures I want. But we need to see if that 3 should stay at 3 or if it should round up to a 4. And so if you remember your rounding rules, if the number to the right of the number you're looking at, so the 3 to the right of it is a 2. If it's less than 5, like 2 is, then we leave it alone. And so my answer would be 2.53. If the number to the right instead is 5 or greater, like for instance this one is 6, then we're going to round it up, so 2.54. So we have measurements now, and normally you don't just report measurements, we want to do some analysis of it. We're going to do some calculations with it. If the calculation that we're doing is addition or subtraction, then the answer that we get once we've plugged all our numbers into the calculator, because the calculator loves to just spit out a huge string of numbers, we're not going to use all of those, because again, the numbers that we report have meaning. And so our answer cannot be more precise than either of our measurements, any of our measurements. So whichever one is the least precise measurement, the answer has to be that same amount of precision. So for addition and subtraction, it's going to have to do with the place that it's at. So if we look at this first example problem here, 54.0 plus 257.12. The 54.0, the last significant figure that I have is this 0 that is in the 10th place. For 257.12, I have the 2, which is in the 100th place. So again, I'm just going to underline those in this problem. I like lining them up because it makes it easy to see where my answer should stop at. So my answer can't be more precise than this least precise measurement, and the least precise measurement is in the 10th place. So my answer is going to stop in that 10th place. So when I add this together, I'm going to get 311.12. That's what the calculator spits out. But remember, I cannot report that 100th place, so I can only report the 10th place. So I look to see if I need to round it, and I don't. So my answer would be 311.1. So same thing with this one. Let's say we don't have any decimal points present. Well, we still have places, right? So 1,250, the last significant digit is in the tens place, In the number 300, the last significant digit is in the hundreds place. So again, my answer would be, the calculator would say it's 1,550, but my answer can only be as precise as my least precise number, and 300 is my least precise number. I can only have it to the hundreds place. So again, I look to see if that 5 is going to remain a 5, and it's not, because there's a 5 next to it. And so my answer would actually be 1,600. So adding, subtracting, it has to do with where the placement of my least precise measurement is. For multiplication and division, it's a little bit, I think, a little bit easier. So what we're looking here is the number of sig figs that are present in my measurements. So for instance, 54.0, the 5, the 4, and the 0 all are significant. So this number has 3 significant figures. 257.12, all of these are non-zero numbers, so they are all significant. This measurement has 5 significant figures. So when I do the calculation, the calculator is going to spit out the number 13,884.48. Now, my answer actually can't have this much significance because the measurements that it's coming from are not that precise. So the one that's least precise has 3 significant figures. And so my answer can only have 3 significant figures. So starting from the left, I'm going to have 1, 2, 3. Only those 3. Do I round this 8 or does it stay the same? Well, next to it is another 8, so I'm going to round it. So my answer is going to be 13,900. Now, I can't just write 139. That's 13,884 does not round to 139, but 13,884 can round to 13,900. And so I'm going to add zeros. Remember, these are not significant because there's no decimal point present. So this answer would actually be reported as 13,900.